Database, ETL/ELT processes, ML, programming patterns, data structures for data engineers. Idempotency is a crucial concept in data engineering table management, especially when dealing with data pipelines and ETL/ELT processes. It ensures that an operation can be applied multiple times without changing the result beyond the initial application. This is essential for building robust and reliable data pipelines that can handle failures and retries gracefully. It basically means that the results of a given output will be the same no matter how many times you run it. Merge is an example. It only appends a record where there is no other row that exists with the same ID. An insert appends the row, repeating whatever values that exists in any other rows. Idempotent is important because in stateful events, you don't want to loop a never-ending copying of data. If it exits, don't append is the rule of thumb. Here's how idempotency plays a role in various aspects of table management. 1. Data ingestion. Handling duplicates. When ingesting data from various sources, idempotent operations help prevent duplicate records from being inserted into the table. This can be achieved through unique constraints, deduplication techniques, or using insert/update statements that only insert new records. Recovery from failures. If a data ingestion process fails midway, idempotency allows you to restart the process without worrying about corrupting the data or creating inconsistencies. The operation can be safely retried, and only the missing data will be processed. 2. Data transformations. Consistent results. Idempotent transformations ensure that applying the same transformation multiple times produces the same result. This is crucial for maintaining data integrity and consistency, especially when dealing with complex transformations or multiple stages of processing. Rerunning pipelines. If a data pipeline needs to be rerun due to errors or updates, idempotent transformations guarantee that the data will be transformed consistently, regardless of how many times the pipeline is executed. 3. Table updates and deletions. Safe updates. Idempotent updates ensure that applying the same update multiple times has the same effect as applying it once. This is useful for handling concurrent updates or recovering from failures during update operations. Controlled deletions. Idempotent deletions prevent accidental data loss by ensuring that deleting the same data multiple times has the same effect as deleting it once. 4. Schema management. Consistent schema evolution. Idempotent schema changes allow you to apply schema migrations multiple times without causing errors or inconsistencies. This is important for managing database schema changes over time, especially in a collaborative environment. Examples of idempotent operations in table management. Insert with unique constraint. If a record with the same unique key already exists, the insert operation will be ignored. Update with a where clause. Only the rows matching the where clause will be updated, even if the update statement is executed multiple times. Delete with a where clause. Only the rows matching the where clause will be deleted. Create table if not exists. If the table already exists, the statement will have no effect. Alter table add column if not exists. If the column already exists, the statement will be ignored. By incorporating idempotency into data engineering table management processes, you can create more resilient, reliable, and maintainable data pipelines that can handle the complexities of modern data environments. Hallucinations in machine learning refer to the phenomenon where a model generates outputs that are factually incorrect or nonsensical, often with high confidence. These outputs are not supported by the input data or the model's training. While hallucinations and idempotency are distinct concepts, they can be related in certain contexts, particularly in the realm of data generation and transformation. Data generation. If an ML model is used to generate data, example text, images, code, hallucinations can lead to inconsistent or unpredictable outputs. This can make it challenging to achieve idempotency, as rerunning the generation process might produce different results due to the model's hallucinatory behavior. For example, if a language model is used to generate product descriptions, hallucinations might lead to different descriptions being generated for the same product each time the model is run. This breaks idempotency, as the operation of generating a description for a given product does not produce the same output consistently. Data transformation. If an ML model is used as part of a data transformation pipeline, hallucinations can introduce errors or inconsistencies in the transformed data. This can affect the idempotency of the pipeline, as rerunning the pipeline might produce different results due to the model's unpredictable behavior. For example, if an ML model is used to classify customer sentiment, hallucinations might lead to different sentiment labels being assigned to the same customer feedback each time the model is run. This breaks idempotency, as the operation of classifying sentiment for a given feedback does not produce the same output consistently. Mitigating hallucinations for idempotency. To ensure idempotency in data pipelines that involve ML models, it's crucial to mitigate hallucinations. Here are some strategies. Improve data quality. Train models on high-quality, diverse data that accurately represents the real-world scenarios the model will encounter. Regularize model training. Use regularization techniques during training to prevent overfitting and encourage the model to generalize better. Ensemble methods. Combine multiple models to reduce the impact of individual model hallucinations. Post-processing and validation. Implement post-processing steps to validate and correct model outputs, ensuring consistency and adherence to expected patterns. Human in the loop, involve human experts in the process to review and correct model outputs, especially in critical applications. By addressing hallucinations, you can improve the reliability and predictability of ML models, making it easier to achieve idempotency in data engineering tasks. This is essential for building robust and trustworthy data pipelines that produce consistent results, regardless of how many times they are executed. Sources and related content. Go and Python design patterns. Pattern category. Python pattern. Go pattern. Description. Creational. Singleton. Singleton. Ensures a class, Python, or struct, Go, has only one instance. Creational. Factory method. Factory method. Defines an interface for creating objects, but lets subclasses/subtypes decide which class/type to instantiate. Creational. Abstract factory. Abstract factory. Provides an interface for creating families of related objects without specifying concrete classes/types. Creational. Builder. Builder. Separates object construction from its representation. Creational. Prototype. Prototype. Creates new objects by cloning a prototypical instance. Structural. Adapter. Adapter. Converts the interface of a class/type into another interface. Structural. Bridge. Bridge. Decouples an abstraction from its implementation. Structural. Composite. Composite. Composes objects into tree structures. Structural. Decorator. Decorator. Dynamically adds responsibilities to an object. Structural. Facade. Facade. Provides a simplified interface to a complex subsystem. Structural. Flyweight. Flyweight. Reduces memory usage by sharing objects. Structural. Proxy. Proxy. Controls access to an object. Behavioral. Chain of responsibility. Chain of responsibility. Passes a request along a chain of handlers. Behavioral. Command. Command. Encapsulates a request as an object. Behavioral. Interpreter. Interpreter. Defines a grammatical representation for a language. Behavioral. Iterator. Iterator. Provides a way to access elements of a collection sequentially. Behavioral. Mediator. Mediator. Centralizes communication between objects. Behavioral. Memento. Memento. Captures and restores an object's internal state. Behavioral. Observer. Observer. Notifies dependents of state changes. Behavioral. State. State. Alters an object's behavior when its state changes. Behavioral. Strategy. Strategy. Defines a family of interchangeable algorithms. Behavioral. Template method. Template method. Defines the skeleton of an algorithm, deferring some steps to subclasses/subtypes. Behavioral. Visitor. Visitor. Adds new operations to a hierarchy without changing the structure. Pipeline or chain of responsibility, for creating a sequence of processing steps, where data flows through each step in a defined order. This is useful for ETL pipelines, data validation, and cleaning workflows. Factory, for creating objects without specifying the exact class of object that will be created. This is helpful for creating data source connections, data formatters, or transformation objects dynamically based on configuration or data characteristics. Singleton, for ensuring that a class has only one instance and providing a global point of access to it. This can be used for managing shared resources like database connections, configuration managers, or logging utilities. Strategy, for defining a family of algorithms, encapsulating each one, and making them interchangeable. This is valuable for implementing different data processing strategies, such as filtering, aggregation, or machine learning model training, and allowing them to be selected at runtime. Template method, for defining the skeleton of an algorithm in an operation, deferring some steps to subclasses. This is useful for defining common data processing workflows with variations in specific steps, such as data extraction or loading. Adapter, for converting the interface of a class into another interface clients expect. This is essential for integrating with different data sources, APIs, or third-party libraries that may have incompatible interfaces. Decorator, for dynamically adding responsibilities to an object. This can be used for adding data validation, logging, or monitoring capabilities to data pipelines without modifying the core processing logic. Facade, for providing a simplified interface to a complex subsystem. This is helpful for interacting with data warehouses, cloud storage systems, or distributed computing frameworks, hiding their complexity behind a unified interface. Composite, for composing objects into tree structures to represent part-whole hierarchies. This is useful for building complex data transformation pipelines or representing hierarchical data structures. Flyweight, for reducing memory usage by sharing objects. This is beneficial when dealing with large volumes of data with repetitive elements, such as sensor data or log files. Proxy, for controlling access to an object. This can be used for implementing security measures, caching, or lazy loading in data access layers. Builder, for separating the construction of a complex object from its representation so that the same construction process can create various representations. This is useful for building complex data structures or query builders. Observer, for defining a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. This can be used for triggering actions based on data changes, such as sending alerts or updating dashboards. Model drift is the constant changing conditions on the ground, news, weather, consumer habits, economic factors, and other unknown factors. ML models require constant training and updating as these conditions change. GAUD data, or ground truth data, in RAG, retrieval augmented generation, domain-specific data that is considered fact, truth, and will likely never drift is often referred to as gold data or ground truth. Gold data, this term emphasizes the high quality and reliability of the data. It's like the gold standard against which other data is measured. Ground truth, this term highlights that the data represents the absolute truth or reality for that specific domain. Characteristics of gold data/ground truth. High accuracy, it's meticulously curated and validated to ensure its accuracy and correctness. Stability, it's unlikely to change or become outdated, representing enduring facts or knowledge. Domain relevance, it's highly relevant to the specific domain and provides essential context for understanding and interpreting other data. Trusted source, it's often sourced from authoritative sources or experts in the field. Examples. Scientific laws and principles, in physics or chemistry, established laws like Newton's laws of motion or the periodic table would be considered gold data. Medical definitions and diagnoses, in healthcare, standardized medical terminologies and diagnostic criteria would be considered ground truth. Legal statutes and regulations, in law, codified laws and regulations represent the ground truth for legal interpretation. Financial regulations and standards, in finance, accounting standards and regulatory frameworks serve as gold data. Importance in RAG. Gold data/ground truth plays a crucial role in RAG systems by providing a reliable knowledge base. It forms the foundation of the knowledge base used for retrieval and augmentation. Improving accuracy and trustworthiness, it helps ensure that the generated responses are accurate, consistent, and aligned with domain expertise. Reducing hallucinations, it minimizes the risk of the language model generating factually incorrect or misleading information. Supporting explainability, it provides a clear and verifiable source for the information used in generating responses. By incorporating gold data/ground truth, RAG systems can achieve higher levels of accuracy, reliability, and trustworthiness, making them more valuable for domain-specific applications. ML Model Serving Pipeline. This document explains the process of serving machine learning models for both online inference, real-time predictions, and batch inference, offline predictions. Online inference. Online inference focuses on providing predictions with low latency, typically for individual requests. Process. Request, a user or system sends a request with input data to the model serving system. Pre-processing, the input data is pre-processed, cleaned, transformed, and featurized, in the same way the training data was. This ensures consistency and that the model understands the input. Model loading, the trained ML model is loaded into memory, if not already, for fast access. Prediction, the model generates a prediction based on the pre-processed input. Post-processing, the prediction may be post-processed, example converting probabilities to labels, formatting, to make it more understandable or usable. Response, the prediction is returned to the user or system. Tools/technologies. Model serving frameworks, TensorFlow serving, Torch serve, KF serving, Triton inference server. Containerization, Docker, Kubernetes. Load balancing, to distribute traffic across multiple model instances. Monitoring and logging, to track performance and identify issues. Example. A fraud detection system that receives credit card transaction details and predicts in real time whether the transaction is fraudulent or not. A recommendation system that suggests products or content to users as they browse a website. Batch inference. Batch inference is optimized for processing large volumes of data and generating predictions in bulk. Process. Data input, a batch of data is loaded from a source, example database, cloud storage. Pre-processing, the entire batch is pre-processed, cleaned, transformed, and featurized, similar to online inference. Model loading, the trained ML model is loaded into memory. Prediction, the model generates predictions for the entire batch of data. Post-processing, the predictions are post-processed, example formatting, aggregating, as needed. Output, the predictions are stored in a destination, example database, cloud storage, or used for further analysis. Tools/technologies. Distributed computing frameworks, Apache Spark, Apache Flink, Dask. Cloud platforms, AWS Batch, Google Cloud Dataflow. Workflow orchestration, Apache Airflow. Data storage, cloud storage, S3, GCS, data warehouses, BigQuery, Snowflake. Example. A customer segmentation system that analyzes customer data and assigns them to different segments for targeted marketing. A churn prediction system that predicts which customers are likely to churn in the near future. Key differences. Feature. Online inference. Batch inference. Latency. Low, real-time. High, can take minutes to hours. Data volume. Single item. Large batch. Use cases. Real-time applications, interactive systems. Offline analysis, reporting, bulk predictions. Tools/technologies. Model serving frameworks, containerization, load balancing. Distributed computing frameworks, cloud platforms, workflow orchestration. One API connectors/wrappers. Fivetran provides pre-built connectors to various data sources, automating extraction and loading into data warehouses. Stitch offers a wide range of integrations for SaaS applications and databases, simplifying data ingestion. Airbyte, an open-source platform with a large catalog of connectors, allowing for custom connector development. Matillion provides a low-code/no-code environment for building data pipelines with pre-built connectors and a visual interface. 2 streaming platforms. Apache Kafka, a distributed streaming platform for handling real-time data streams from various sources. Amazon Kinesis, a managed streaming service for collecting, processing, and analyzing real-time data. Google Cloud Dataflow, a fully managed service for batch and stream data processing, offering high scalability and flexibility. 3 ETL/ELT tools. Informatica Power Center, a comprehensive ETL tool with a wide range of connectors and transformations for data integration. Tailend, an open-source data integration platform with a visual designer and support for various data sources. AWS Glue, a serverless ETL service that automates data discovery, transformation, and loading. 1 open-source options. Apache Spark SQL. Spark itself has powerful built-in features for ETL through Spark SQL. You can use SQL-like queries or data frames to perform transformations, aggregations, and data manipulation. It's highly scalable and integrates seamlessly with other Spark components. Pros: cost-effective, highly scalable, excellent performance, integrates with the Spark ecosystem. Cons: requires coding, SQL or Python/Scala/Java, steeper learning curve for beginners. dbt, data build tool. While not strictly an ETL tool, dbt is fantastic for the T and ELT. It uses SQL to define transformations and build data models, making it very efficient for data analysts and engineers familiar with SQL. It works well with Spark and data warehouses like Snowflake, BigQuery, and Redshift. Pros: SQL-based, promotes code reusability and testing, good for data modeling, strong community support. Cons: primarily focused on transformations, less suited for complex extraction or loading tasks. 2 commercial options. Databricks, built on top of Spark, Databricks provides a managed environment for data engineering, including ETL/ELT. It offers a collaborative workspace, optimized Spark runtime, and integrations with various data sources. Pros: managed Spark environment, easy to use, collaborative features, good for large-scale data processing. Cons: can be expensive, vendor lock-in. Tailend, an open-source and commercial data integration platform that supports Spark for large-scale data processing. It offers a visual designer, pre-built components, and connectors to various data sources. Pros: visual interface, wide range of connectors, supports both ETL and ELT, good for complex pipelines. Cons: can be complex to learn, open-source version has limitations. Informatica Power Center, a mature and widely used ETL tool that supports Spark as an execution engine. It offers a comprehensive set of features for data integration, transformation, and quality management. Pros: powerful and feature-rich, good for enterprise-level ETL, extensive connectivity. Cons: can be expensive, complex to learn and manage. 3 cloud-native options. AWS Glue, a serverless ETL service from AWS that can run Spark jobs for data processing. It integrates well with other AWS services and offers a visual interface for building ETL workflows. Pros: serverless, cost-effective, integrates with AWS ecosystem, good for cloud-based data lakes. Cons: limited customization compared to other tools, vendor lock-in. Google Cloud Dataflow, a fully managed service for batch and stream data processing on Google Cloud. It's based on Apache Beam and can execute Spark pipelines for large-scale data transformations. Pros: highly scalable, serverless, supports both batch and streaming, good for real-time data pipelines. Cons: can be expensive for high-volume processing, vendor lock-in. Key considerations when choosing your existing tech stack. Choose a tool that integrates well with your current data sources, storage systems, and processing frameworks. Ease of use: consider the learning curve and the level of technical expertise required to use the tool. Scalability and performance: ensure the tool can handle the volume and velocity of your data. Cost: evaluate the pricing model and whether it aligns with your budget. Community and support: look for tools with active communities and good vendor support. For cloud-specific data transfer services. AWS Data Pipeline, a web service for automating data movement between AWS services and on-premises resources. Google Cloud Storage Transfer Service, a fully managed service for transferring data to Google Cloud Storage from various sources. Azure Data Factory, a cloud-based data integration service for creating ETL and ELT pipelines. 5 API management platforms. Apigee, a platform for managing and securing APIs, providing features like rate limiting, authentication, and analytics. MuleSoft Endpoint Platform, a platform for connecting applications, data, and devices through APIs, offering tools for API design, management, and monitoring. Kong, an open-source API gateway for managing, securing, and extending APIs. Choosing the right tool depends on several factors. Data sources, the types and number of data sources you need to integrate. Data volume and velocity, the volume and speed of data ingestion. Pipeline complexity, the complexity of the data transformations and workflows. Scalability and performance, the scalability requirements and desired performance. Budget and resources, the available budget and technical expertise. By carefully evaluating these factors and considering the strengths and weaknesses of each tool, data engineers can select the most suitable API tools to manage their data ingestion processes effectively. Q&A. What are design patterns and why are they important? Design patterns are reusable solutions to common problems in software design. They provide a vocabulary and a framework for developers to communicate about and implement well-established solutions. They promote code reusability, maintainability, and scalability, allowing for better software architecture by leveraging proven approaches. The video emphasizes their enduring relevance even in a rapidly changing tech landscape. What is the factory pattern and how does it simplify object creation? The factory pattern abstracts the instantiation logic away from the client code. Instead of directly creating objects, you ask a factory to create them for you, providing the necessary parameters. This pattern allows for easier object creation management, especially when dealing with multiple types of similar objects. For example, you can ask a burger factory for a cheeseburger, a deluxe cheeseburger or a vegan burger without needing to know how the object is constructed and what ingredients are used. How does the builder pattern provide more control over object construction compared to the factory pattern? The builder pattern provides a step-by-step approach to object construction. Instead of passing all parameters at once, like a factory, a builder allows you to add individual ingredients, or set properties, incrementally through method chaining. The build method generates the final object. This is particularly useful when dealing with complex objects with many optional parameters, offering better control and more readable code. What does the singleton pattern ensure, and how is it implemented? The singleton pattern ensures that a class only has one instance throughout its lifetime. This is useful for managing resources or application states that must be shared across different parts of an application. The implementation involves a static instance variable to store the one instance and a static method that checks if an instance exists. If it doesn't, the method creates the instance, and if it does, it returns the existing one. Can you explain the observer pattern and how it is used for real-time updates? The observer, or pub/sub, pattern enables a one-to-many dependency between objects. A subject, publisher, maintains a list of observers, subscribers. When the subject's state changes, it notifies all its subscribers. This allows components to react to updates dynamically and in real time. An example is a YouTube channel, subject, notifying its subscribers, observers, when a new video is uploaded. What is the iterator pattern and what problem does it solve? The iterator pattern provides a way to access the elements of a collection sequentially without exposing its underlying structure. Instead of directly indexing or manipulating pointers, one can use an iterator to move through the collection and access each item one by one. This is particularly useful with collections that have complex storage structures, linked lists, binary search trees, etc. How does the strategy pattern enable flexible algorithm selection at runtime? The strategy pattern defines a family of algorithms, strategies, and encapsulates each one into separate classes. A client can choose which algorithm, strategy, to use at runtime without modifying the client's behavior. This pattern promotes code reuse, flexibility, and adhere to the open-closed principle. For instance, filtering an array can be done using different strategies, such as removing positive or odd values without changing the values class. What is the role of the adapter pattern and how does it bridge incompatibilities? The adapter pattern allows two incompatible interfaces to work together by acting as a bridge between them. It wraps an existing class with a new interface, making it compatible with a client that expects a different one. In the video, a micro USB cable is adapted to a USB port using an adapter that acts as a bridge between these two incompatible interfaces. This prevents incompatible systems from disrupting functionality and avoids the need for the client code to be changed. Pipeline or chain of responsibility, for creating a sequence of processing steps, where data flows through each step in a defined order. This is useful for ETL pipelines, data validation, and cleaning workflows. Factory, for creating objects without specifying the exact class of object that will be created. This is helpful for creating data source connections, data formatters, or transformation objects dynamically based on configuration or data characteristics. Singleton, for ensuring that a class has only one instance and providing a global point of access to it. This can be used for managing shared resources like database connections, configuration managers, or logging utilities. Strategy, for defining a family of algorithms, encapsulating each one, and making them interchangeable. This is valuable for implementing different data processing strategies, such as filtering, aggregation, or machine learning model training, and allowing them to be selected at runtime. Template method, for defining the skeleton of an algorithm in an operation, deferring some steps to subclasses. This is useful for defining common data processing workflows with variations in specific steps, such as data extraction or loading. Adapter, for converting the interface of a class into another interface clients expect. This is essential for integrating with different data sources, APIs, or third-party libraries that may have incompatible interfaces. Decorator, for dynamically adding responsibilities to an object. This can be used for adding data validation, logging, or monitoring capabilities to data pipelines without modifying the core processing logic. Facade, for providing a simplified interface to a complex subsystem. This is helpful for interacting with data warehouses, cloud storage systems, or distributed computing frameworks, hiding their complexity behind a unified interface. Composite, for composing objects into tree structures to represent part-whole hierarchies. This is useful for building complex data transformation pipelines or representing hierarchical data structures. Flyweight, for reducing memory usage by sharing objects. This is beneficial when dealing with large volumes of data with repetitive elements, such as sensor data or log files. Proxy, for controlling access to an object. This can be used for implementing security measures, caching, or lazy loading in data access layers. Builder, for separating the construction of a complex object from its representation so that the same construction process can create various representations. This is useful for building complex data structures or query builders. Observer, for defining a one-to-many dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. This can be used for triggering actions based on data changes, such as sending alerts or updating dashboards. Creational patterns. Factory, this pattern is used when you want to create an object, like a burger, without having to worry about the details of how it's made one. The factory instantiates the object and returns it. For example, you can tell the factory what kind of burger you want, and it will create it for you. Factory pattern use cases for data engineers. The factory pattern is particularly useful when uncertainties in the type of objects. Data source abstraction. Imagine a data pipeline that can ingest data from various sources, CSV files, JSON files, SQL databases, APIs, etc. A factory can create the appropriate data reader object based on the source type specified in a configuration file or at runtime. Example, a data source factory could take a source type, CSV, SQL, API, and return a CSV reader, SQL reader, or API reader object, respectively. This hides the complexity of object creation from the pipeline. Data format handling. Data engineers often deal with diverse data formats, Parquet, Avro, ORC. A factory can create the correct data format writer/reader based on the desired format. Example, a data format factory could create Parquet writer, Avro reader, etc. Decisions to be made at runtime regarding what classes to use. Dynamic pipeline configuration. A data pipeline might need to adapt its processing steps based on runtime conditions, example data volume, available resources, error rates. A factory can dynamically create the necessary processing module objects. Example, a processing module factory could create a fast aggregation module or a detailed analysis module depending on the current workload. Environment-specific configurations. Data pipelines often run in different environments, development, staging, production. A factory can create objects tailored to the specific environment's configurations. Example, a storage client factory could create an ADLS client, Azure Data Lake Storage, in the production environment and an S3 client, Amazon S3, in a test environment. Defines an interface for creating objects, but lets subclasses/subtypes decide which class/type to instantiate. Extensible data transformation pipelines. A data transformation pipeline might need to support various transformation operations, example data cleansing, feature engineering, aggregation. A factory can provide a base interface for transformation operations and let subclasses implement specific transformations. Example, a transformation factory could define a create_transformation method, and subclasses like cleanse transformation factory or aggregate transformation factory would create specific transformation objects. This allows for easy addition of new transformations without modifying the core pipeline. Plugin systems. Data engineers can make use of plugin systems that allow for the dynamic addition of new features to a data processing system. A factory pattern can be used to create the objects that are used by the plugin system. Addressing other scenarios. When you want to allow only one object to be instantiated from a class. This is the singleton pattern, not the factory pattern. While data engineers might use singletons, example for a global configuration object, it's a separate concern. Example, a database connection pool could be implemented as a singleton. In essence, the factory pattern helps data engineers write more flexible, maintainable, and extensible code by abstracting the object creation process. This is critical in the dynamic and evolving world of data engineering. Factory. Class burger. Def__init__, self, ingredients. Self.ingredients equals ingredients. Def print, self. Print, self.ingredients. Class burger factory. Def create cheeseburger, self. Ingredients equals bun, cheese, beef patty. Return burger, ingredients. Def create deluxe cheeseburger, self. Ingredients equals bun, tomato, lettuce, cheese, beef patty. Return burger, ingredients. Def create vegan burger, self. Ingredients equals bun, special sauce, veggie patty. Return burger, ingredients. Burger factory equals burger factory. Burger factory.create cheeseburger.print. Burger factory.create deluxe cheeseburger.print. Burger factory.create vegan burger.print. Output. Bun, cheese, beef patty. Bun, tomato, lettuce, cheese, beef patty. Bun, special sauce, veggie patty. Builder, this pattern provides more control over how an object is created. 3. Instead of passing in all the parameters at once, you use a builder object. 3. The builder has individual methods for adding each part of the object, and these methods can be chained together. 3. Finally, the build method is called, which returns the final product. 4. Builder pattern use cases for data engineers. Complex data pipeline configurations. Data pipelines often involve numerous configuration parameters, data source paths, transformation steps, output destinations, resource allocations, error handling policies, and more. Using a builder pattern allows data engineers to construct these configurations step by step, making the code more readable and maintainable. Example. A pipeline configuration builder could have methods like set source path, add transformation, set output format, and set resource allocation, CPU, memory. This allows for the creation of various pipeline configurations with different combinations of parameters. This helps when data pipelines are configured via code, instead of configuration files. Building complex data transformation objects. Data transformations can be intricate, involving multiple stages and parameters. The builder pattern allows data engineers to build these transformation objects incrementally, ensuring that all necessary parts are included. Example. A feature engineering builder could have methods like add imputation, column, strategy, add scaling, column, method, and add polynomial features, column, degree. This provides a structured way to define complex feature engineering pipelines. Constructing data serialization/deserialization objects. When dealing with data serialization, example converting data to JSON or Avro, data engineers often need to configure various serialization options. The builder pattern can simplify the construction of these serialization objects. Example. A Avro schema builder could have methods like add field, name, type, set namespace, and set doc. This makes it easier to define complex Avro schemas programmatically. Creating database connection objects. Database connection objects can have numerous configuration parameters, such as connection strings, credentials, timeouts, and connection pool settings. The builder pattern provides a clean way to construct these connection objects. Example. A database connection builder could have methods like set connection string, set username, set password, and set connection pool size. This improves the readability and maintainability of database connection code. Generating complex SQL queries. Data engineers frequently work with complex SQL queries that involve multiple joins, filters, and aggregations. The builder pattern can be used to construct these queries step by step. Example. A SQL query builder could have methods like select, columns, from table, where, condition, and group by, columns. This allows for the dynamic construction of complex SQL queries. API request objects. When working with APIs, data engineers often need to create complex request objects with various headers, parameters, and payloads. Example. An API request builder could have methods like setEndpoint, URL, addHeader, key, value, addParameter, key, value, and setPayload, data. Key benefits for data engineers. Improved readability. The builder pattern makes complex object creation code more readable and understandable. Reduced complexity. It simplifies the construction of objects with many optional or interdependent parameters. Enhanced maintainability. It makes it easier to modify and extend complex object creation logic. Flexibility. It allows for the creation of different variations of an object using the same builder. Prevents telescoping constructors. Avoids constructors with many parameters that are hard to understand and maintain. Builder. Class Burger. Def __init___ self. Self.buns equals none. Self.patty equals none. Self.cheese equals none. Def set buns, self, buns tile. Self.buns equals buns tile. Def set patty, self, patty style. Self.patty equals patty style. Def set cheese, self, cheese style. Self.cheese equals cheese style. Class Burger Builder. Def __init___ self. Self.burger equals burger. Def add buns, self, buns tile. Self.burger.set buns, buns tile. Return self. Def add patty, self, patty style. Self.burger.set patty, patty style. Return self. Def add cheese, self, cheese style. Self.burger.set cheese, cheese style. Return self. Def build, self. Return self.burger. Burger equals burger builder, backslash. Dot add buns, sesame, backslash. Dot add patty, fish patty, backslash. Dot add cheese, Swiss cheese, backslash. Dot build. Singleton. This pattern ensures that a class can only have one instance 5. It is useful for maintaining a single copy of an application's state 5. A static method checks if an instance exists, and if not, creates one 6. If an instance exists, the method returns the existing instance 6. Singleton pattern use cases for data engineers. Database connection pools. Maintaining a single connection pool across an application or service is crucial for efficient database interaction. Creating multiple connection pools would waste resources and potentially lead to connection exhaustion. A singleton ensures that all parts of the application use the same connection pool, optimizing database interactions. Configuration managers. Data pipelines and applications often rely on configuration settings, example database credentials, file paths, API keys. A singleton configuration manager ensures that all components of the system access the same, consistent configuration. This prevents inconsistencies and simplifies configuration management. Logging services. Centralized logging is essential for monitoring and debugging data pipelines and applications. A singleton logging service ensures that all log messages are written to the same log file or destination, maintaining a consistent log stream. This makes it easier to track events and diagnose issues. Resource managers. Data pipelines might need to manage shared resources, such as distributed caches or message queues. A singleton resource manager can ensure that these resources are accessed and managed consistently by all components of the system. This prevents resource conflicts and ensures efficient resource utilization. Distributed cache clients. When working with distributed caching systems, example Redis, MEMC8, a single client instance is typically used to connect to the cache. A singleton ensures that all parts of the application use the same cache client, avoiding unnecessary connections and improving performance. Spark session management. In Spark applications, creating multiple Spark session instances can lead to resource conflicts and performance issues. A singleton can be used to ensure that only one Spark session is created and shared across the application. This optimizes resource utilization and simplifies Spark application development. Metadata repositories. Data engineers may need to access a central metadata repository to retrieve information about data assets, pipelines, or transformations. A singleton metadata repository client can ensure that all components of the system access the same, consistent metadata. Key considerations. Overuse. The singleton pattern should be used judiciously. Overuse can lead to tightly coupled code and make it difficult to test. Thread safety. When using singletons in multi-threaded environments, it's essential to ensure thread safety to prevent race conditions. Testing. Singletons can make unit testing more difficult, as they introduce global state. Consider dependency injection as an alternative if testability is a primary concern. Alternatives. Dependency injection is often preferred over singletons, as it provides greater flexibility and testability. Singleton. Class application state. Instance equals none. Def underscore underscore init underscore underscore self. Self dot is logged in equals false. At static method. Def get app state. If not application state dot instance. Application state dot instance equals application state. Return application state dot instance. App state 1 equals application state dot get app state. Print app state 1 dot is logged in. App state 2 equals application state dot get app state. App state 1 dot is logged in equals true. Print app state 1 dot is logged in. Print app state 2 dot is logged in. Behavioral patterns. Observer, also known as the pub/sub pattern, this pattern is used when multiple objects need to be notified of events in real time. 7. The subject, publisher, maintains a list of observers, subscribers. 8. When an event occurs, the subject notifies all the subscribers. 9. Observer pattern use cases for data engineers. Real-time data monitoring and alerting. Imagine a data pipeline ingesting streaming data from various sources. You want to monitor this data for anomalies, errors, or specific conditions in real time. The observer pattern can be used to implement a monitoring system where the data pipeline acts as the subject, publisher, emitting events like data quality issue, pipeline error, or threshold exceeded. Various observers, subscribers, can be attached. An alerting system that sends notifications, example email, Slack, when critical events occur. A dashboard that visualizes real-time data quality metrics. A logging system that records events for auditing or debugging. Triggering downstream processes. In a complex data pipeline, the completion of one stage might trigger the execution of subsequent stages. The observer pattern can be used to orchestrate these dependencies. The completion of a data processing stage acts as an event, published by the subject. Downstream stages, observers, are triggered automatically when the event is received. Example. A data ingestion stage, subject, publishes an ingestion complete event. A data transformation stage, observer, subscribes to this event and starts its processing when the event is received. Real-time analytics dashboards. When building real-time analytics dashboards, the observer pattern can be used to update the dashboard with fresh data as it arrives. The data stream acts as the subject, publishing events containing new data points or aggregated metrics. The dashboard components, observers, subscribe to these events and update their visualizations accordingly. Microservices communication. In a microservices architecture, services often need to communicate with each other in real time. The observer pattern can facilitate this communication. Services can publish events related to their operations, example, order created, payment processed. Other services can subscribe to these events and react accordingly. Data governance and auditing. To track data lineage and ensure compliance, data engineers can use the observer pattern to monitor data access and transformations. Data access events, example data read, data modified, can be published by the subject, data store or pipeline. Observers can log these events, perform audits, or enforce data governance policies. Event-driven data pipelines. Modern data architectures often employ event-driven processing, where data pipelines react to events rather than following a fixed schedule. The observer pattern is a natural fit for this paradigm, allowing pipelines to subscribe to relevant events and trigger processing accordingly. Key benefits for data engineers. Loose coupling. The observer pattern promotes loose coupling between components, making the system more flexible and maintainable. Real-time responsiveness. It enables real-time reactions to events, which is crucial for many data engineering applications. Scalability. The pub/sub model can be scaled to handle a large number of observers and events. Extensibility. It's easy to add new observers or events without modifying existing code. By leveraging the observer pattern, data engineers can build more responsive, scalable, and event-driven data systems. Behavioral patterns. Observer/pub/sub. It's common for different components of an app to respond to events or state changes, but how can we communicate these events? The observer pattern is a popular solution. We have a subject, aka publisher, which will be the source of events. And we could have multiple observers, aka subscribers, which will receive events from the subject in real time. Class YouTube channel. Def underscore underscore init underscore underscore self name. Self.name equals name. Self.subscribers equals def subscribe self sub. Self.subscribers.append sub. Def notify self event. For sub in self.subscribers. Sub.send notification, self.name, event. From ABC import ABC, abstract method. Class YouTube subscriber, ABC. Add abstract method. Def send notification, self, event. Pass. Class YouTube user, YouTube subscriber. Def underscore underscore init underscore underscore, self, name. Self.name equals name. Def send notification, self, channel, event. Print, f, user self.name received notification from channel, event. Channel equals YouTube channel, need code. Channel.subscribe, YouTube user, sub 1. Channel.subscribe, YouTube user, sub 2. Channel.subscribe, YouTube user, sub 3. Channel.notify, a new video released. In this case we have multiple subscribers listening to a single published. But users could also be subscribed to multiple channels. Since the publishers and subscribers don't have to worry about each other's implementations, they are loosely coupled. User sub 1 received notification from need code, a new video released. User sub 2 received notification from need code, a new video released. User sub 3 received notification from need code, a new video released. Iterator, this pattern defines how the values in an object can be iterated through 10. It provides a simple interface for accessing the values of a complex object like a linked list without needing to worry about pointer manipulation. 11. Iterator pattern use cases for data engineers. Processing large datasets in chunks. Data engineers often work with datasets that are too large to fit in memory. The iterator pattern allows them to process these datasets in smaller, manageable chunks. Example. Reading a large CSV file from cloud storage, an iterator can be used to read the file row by row or in batches, without loading the entire file into memory. This prevents memory issues and allows for efficient processing of massive datasets. Traversing complex data structures. Data engineers sometimes deal with complex data structures like nested JSON objects, XML documents, or custom data formats. The iterator pattern provides a standardized way to traverse these structures, regardless of their internal complexity. Example. Navigating a deeply nested JSON object representing a product catalog, an iterator can be used to access each product's details without writing complex recursive code. Data transformation pipelines. In data transformation pipelines, data often flows through multiple stages of processing. Iterators can be used to pass data between these stages in a controlled and efficient manner. Example. An iterator can feed data to a transformation function one record at a time, allowing for efficient processing and memory management. Custom data source readers. Data engineers might need to create custom data source readers for proprietary file formats or APIs. The iterator pattern can be used to provide a consistent interface for accessing data from these sources, regardless of their underlying implementation. Example. A custom reader for a compressed data format can use an iterator to decompress and return data in chunks. Streaming data processing. In streaming data pipelines, data arrives continuously. Iterators can be used to process this data incrementally, without needing to buffer large amounts of data in memory. Example. An iterator can be used to read data from a Kafka topic one message at a time, allowing for real-time processing. Key benefits for data engineers. Efficiency. Iterators enable efficient processing of large datasets and complex data structures by providing access to data in manageable chunks. Abstraction. They hide the internal complexity of data structures, making it easier to work with them. Standardization. They provide a consistent interface for accessing data from various sources. Flexibility. They allow for different iteration strategies, example forward, backward, filtered. By leveraging the iterator pattern, data engineers can build more efficient, scalable, and maintainable data processing pipelines. Iterator. Many objects in Python have built-in iterators. That's why we can conveniently iterate through an array using the keyword in. MyList equals 1, 2, 3. For n in MyList. Print, n. Output. 1, 2, 3. For more complex objects, like linked lists or binary search trees, we can define our own iterators. Class list node. Def underscore underscore init underscore underscore, self, val. Self.val equals val. Self.next equals none. Class linked list. Def underscore underscore init underscore underscore, self, head. Self.head equals head. Self.cur equals none. Hashtag define iterator. Def underscore underscore iter underscore underscore, self. Self.cur equals self.head. Return self. Hashtag iterate. Def underscore underscore next underscore underscore, self. If self.cur. Val equals self.cur.val. Self.cur equals self.cur.next. Return val. Else. Raise stop iteration. Hashtag initialize linked list. Head equals list node, 1. Head.next equals list node, 2. Head.next.next equals list node, 3. MyList equals linked list, head. Hashtag iterate through linked list. For n in MyList. Print, n. Output. 1, 2, 3. Strategy. This pattern allows you to modify or extend the behavior of a class without directly changing it. 13. You can define different strategies and pass them into the class at runtime. 14. Use case. Data validation with pluggable strategies. Scenario. Imagine a data pipeline that ingests data from various sources. The validation rules for the data might differ depending on the source. For example, data from a financial system might require stricter validation than data from a social media feed. Applying the strategy pattern. Define a validation strategy interface, create an interface, or abstract class, that defines a validate data method. This method takes the data to be validated as input and returns a Boolean indicating whether the data is valid. Create concrete validation strategies, implement different validation strategies as concrete classes that implement the validation strategy interface. Strict validation strategy implements rigorous checks for data types, ranges, and consistency. Lenient validation strategy performs basic checks, allowing for more flexibility in the data. Custom validation strategy implements custom validation rules specific to a particular data source. Data validator class. Create a data validator class that takes a validation strategy object as a parameter, either in the constructor or through a setter method. The data validator's validate data method delegates the validation logic to the injected strategy. Runtime strategy selection. At runtime, based on the data source or other factors, the data engineer can select the appropriate validation strategy and pass it to the data validator. Example code. Conceptual. Python. Hashtag validation strategy interface. Class validation strategy. Def validate, self, data. Raise not implemented error. Hashtag concrete strategies. Class strict validation strategy, validation strategy. Def validate, self, data. Hashtag perform strict validation checks. Hashtag. Return is underscore valid. Class lenient validation strategy, validation strategy. Def validate, self, data. Hashtag perform basic validation checks. Hashtag. Return is underscore valid. Hashtag data validator class. Class data validator. Def underscore underscore init underscore underscore self strategy validation strategy. Self dot strategy equals strategy. Def validate self data. Return self dot strategy dot validate data. Hashtag usage. If data underscore source equals financial system. Strategy equals strict validation strategy. If data underscore source equals social media. Strategy equals lenient validation strategy. Else. Strategy equals custom validation strategy. Validator equals data validator, strategy. Is underscore valid equals validator dot validate, data. Benefits for data engineers. Flexibility, easily switch between different validation strategies at runtime without modifying the data validator class. Maintainability, adding new validation strategies is simple, just create a new class implementing the validation strategy interface. Strategy. A class may have different behavior, or invoke a different method based on something we define, i.e. a strategy. For example, we can filter an array by removing positive values, or we could filter it by removing all odd values. These are two filtering strategies we could implement, but we could add many more. From ABC import ABC, abstract method. Class filter strategy, ABC. Add abstract method. Def remove value, self, val. Pass. Class remove negative strategy, filter strategy. Def remove value, self, val. Return val 0. Class remove odd strategy, filter strategy. Def remove value, self, val. Return ABS, val, %2. Class values. Def underscore underscore init underscore underscore, self, vals. Self.vals equals vals. Def filter, self, strategy. Res equals. For n in self.vals. If not strategy.remove value, n. Res.append, n. Return res. Values equals values, -7, -4, -1, 0, 2, 6, 9. Print, values.filter, remove negative strategy. Print, values.filter, remove odd strategy. Copy. Output. 0, 2, 6, 9. -4, 0, 2, 6. A common alternative to this pattern is to simply pass in an inline/lambda function, which allows us to extend the behavior of a method or class. Use case, flexible data transformation pipelines. Imagine a data engineer is building a data ingestion pipeline. This pipeline needs to handle various data sources, each requiring different transformation rules before loading into a data warehouse. Problem. Diverse data sources. The pipeline receives data from CSV files, JSON APIs, and database dumps. Varying transformation needs. CSV files might need date format conversions and column renaming. JSON APIs might require flattening nested structures and extracting specific fields. Database dumps might need data type casting and filtering. Maintainability and extensibility. The data engineer wants to avoid creating a monolithic pipeline with complex conditional logic, as adding new data sources and transformations would become cumbersome. Solution: the strategy pattern. The data engineer can apply the strategy pattern to decouple the transformation logic from the core ingestion pipeline. Implementation. Define a transformation strategy interface. Python. From ABC import ABC, abstract method. Class transformation strategy, ABC. Add abstract method. Def transform, self, data. Pass. Implement concrete transformation strategies. Python. Import pandas as PD. Import JSON. Class CSV transformation strategy. Def transform, self, data. Hashtag example, convert date column and rename a column. df equals PD data frame, data. If date underscore column and df dot columns. df date underscore column equals PD to underscore data time, df date underscore column. If old underscore name and df dot columns. df dot rename, columns equals old underscore name, new underscore name, in place equals true. Return df. Class JSON transformation strategy. Def transform, self, data. Hashtag example, flatten and extract fields. Flattened underscore data equals. For item in data. Flattened equals. For key, value in item.items. If instance, value, dict. For sub underscore key, sub underscore value in value.items. Flattened f, key underscore sub underscore key equals sub underscore value. Else. Flattened key equals value. Flattened underscore data dot append, flattened. Return flattened underscore data. Class database transformation strategy. Def transform, self, data. Hashtag example, cast data types and filter. df equals PD data frame, data. If numeric underscore column and df dot columns. df numeric underscore column equals PD to underscore numeric, df numeric underscore column. df equals df filter underscore column 10. Return df. Create an ingestion pipeline class. Python. Class data ingestion pipeline. Def underscore init underscore self, transformation underscore strategy. Self.transformation underscore strategy equals transformation underscore strategy. Def ingest underscore n underscore transform, self, data. Transformed underscore data equals self.transformation underscore strategy dot transform, data. Hashtag load transformed underscore data into data warehouse. Print, transformed underscore data. Return transformed underscore data. Use the pipeline with different strategies. Python. CSV underscore data equals date underscore column, 2023-10-26, old underscore name, 10, date underscore column, 2023-10-27, old underscore name, 20. JSON underscore data equals user, ID, 1, name, Alice, order underscore ID, 100, user, ID, 2, name, Bob, order underscore ID, 200. DB underscore data equals numeric underscore column, 5, filter underscore column, 15, numeric underscore column, 12, filter underscore column, 5. CSV underscore pipeline equals data ingestion pipeline, CSV transformation. CSV underscore pipeline dot ingest underscore n underscore transform, CSV underscore data. JSON underscore pipeline equals data ingestion pipeline, JSON transformation. JSON underscore pipeline dot ingest underscore n underscore transform, JSON underscore data. DB underscore pipeline equals data ingestion pipeline, database transformation. DB underscore pipeline dot ingest underscore n underscore transform, DB underscore data. Benefits. Flexibility, easily switch transformation logic at runtime. Maintainability, each transformation strategy is isolated, making it easier to modify or debug. Extensibility, adding new data sources or transformation rules is straightforward by creating new strategy classes. Reduced complexity, avoids large, complex conditional statements in the main pipeline. Code reusability, transformation strategies can be reused across different pipelines. In this scenario, the strategy pattern enables the data engineer to create a robust and adaptable data ingestion pipeline, crucial for handling the dynamic nature of data in modern systems. Facade. This pattern provides a simplified interface to a complex subsystem 16. The facade hides the complexity and makes it easier to use the subsystem 17. Examples include HTTP clients or arrays use case, simplified media file conversion. Imagine an engineer is building an application that needs to handle various media file conversions, example video transcoding, audio format changes, image resizing. The underlying media processing library is powerful but complex, with numerous configuration options and steps. Problem. Complex subsystem. The media processing library has many modules for different tasks, each with its own API. Configuration overload. Users need to understand numerous configuration parameters to perform even simple conversions. Steep learning curve. Developers find it difficult to integrate the library into their applications. Increased code complexity. Directly using the library leads to verbose and hard-to-maintain code. Solution. The facade pattern. The engineer can create a facade that provides a simplified interface to the complex media processing subsystem. Implementation. Complex subsystem, simplified representation. Python. Class video converter. Def convert underscore format, self, input underscore file, output underscore file, codec. Print, f, converting video input underscore file to output underscore file with codec. Hashtag complex video conversion logic. Class audio converter. Def convert underscore sample rate, self, input underscore file, output underscore file, sample rate. Print, f, converting audio input underscore file to output underscore file with sample rate. Hashtag complex audio conversion logic. Class image resizer. Def resize underscore image, self, input underscore file, output underscore file, width, height. Print, f, resizing image input underscore file to output underscore file with dimensions width x height. Hashtag complex image resizing logic. Facade class. Python. Class media converter facade. Def underscore init underscore, self. Self.video underscore converter equals video converter. Self.audio underscore converter equals audio converter. Self.image underscore resizer equals image resizer. Def convert underscore video, self, input underscore file, output underscore file, codec equals H.264. Self.video underscore converter.convert underscore format, input underscore file, output underscore file, codec. Def convert underscore audio, self, input underscore file, output underscore file, sample rate equals 44100. Self.audio underscore converter.convert underscore sample rate, input underscore file, output underscore file, sample rate. Def resize underscore image, self, input underscore file, output underscore file, width equals 800, height equals 600. Self.image underscore resizer.resize underscore image, input underscore file, output underscore file, width, height. Client code, simplified usage. Python. Facade equals media converter facade. Facade.convert underscore video, input.mp4, output.avi. Facade.convert underscore audio, input.wave, output.mp3. Facade.resize underscore image, input.jpg, output.png. Benefits. Simplified interface. The media converter facade provides a clean and easy to use interface, hiding the complexity of the underlying subsystem. Reduced complexity. Client code becomes much simpler and more readable. Decoupling. Changes to the underlying subsystem do not affect client code, as long as the facade interface remains the same. Improved maintainability. The facade centralizes the logic for interacting with the subsystem, making it easier to maintain and update. Easier onboarding. New developers can quickly understand and use the media processing functionality through the simplified facade. In this example, the facade pattern simplifies the use of a complex media processing library, making it more accessible and maintainable for the engineer and other developers. Structural patterns. Facade. According to Oxford Languages, a facade is an outward appearance that is maintained to conceal a less pleasant or creditable reality. In the programming world, the outward appearance is the class or interface we interact with as programmers. And the less pleasant reality is the complexity that is hidden from us. So a facade is simply a wrapper class that can be used to abstract lower-level details that we don't want to worry about. Hashtag Python arrays are dynamic by default, but this is an example of resizing. Class array. Def underscore init underscore, self. Self.capacity equals 2. Self.length equals 0. Self.arr equals 0 asterisk 2 hashtag array of capacity equals 2. Hashtag insert n in the last position of the array. Def pushback, self, n. If self.length equals self.capacity. Self.resize. Hashtag insert at next empty position. Self.arr self.length equals n. Self.length plus equals 1. Def resize, self. Hashtag create new array of double capacity. Self.capacity equals 2 asterisk self.capacity. New ARR equals 0 asterisk self.capacity. Hashtag copy elements to new ARR. For I in range, self.length. New ARRI equals self.arri.
Self.arr equals new ARR.
Hashtag remove the last element in the array. Def popback, self. If self.length 0. Self.length dash equals 1. Adapter, this structural pattern makes incompatible interfaces compatible 14. It is used when a class needs to work with another class that has a different interface 15. The adapter wraps the incompatible class to make it work with the other class 16. Use case, connecting a legacy database to a Spark-based ETL process. Imagine a data engineer is building a modern, scalable ETL, extract, transform, load, pipeline using Apache Spark. However, they need to integrate data from a legacy database that has a unique and incompatible API. Problem: incompatible interfaces. The Spark pipeline expects data sources to provide data in a specific format, example is data frames, or roads. The legacy database has its own custom API for querying and retrieving data, which doesn't align with Spark's expectations. Avoid modifying legacy code. The data engineer cannot or does not want to modify the legacy database's code directly. Maintainability and extensibility. They want to avoid tightly coupling the Spark pipeline to the legacy system, making it easier to replace or update the legacy source in the future. Solution: the adapter pattern. The data engineer can create an adapter that wraps the legacy database's API, making it compatible with Spark's data source interface. Implementation: legacy database API, simplified representation. Python. Class legacy database API. Def query underscore data, self, query. Hashtag simulate a legacy database query. If query equals, select asterisk from legacy underscore table. Return. Legacy underscore ID, 1, legacy underscore value, A. Legacy underscore ID, 2, legacy underscore value, B. Else. Return. Target interface, Spark data source. Python. Hashtag simulate a Spark-like data source interface. Class Spark data source. Def get underscore data underscore as underscore RDD, self. Pass hashtag this would normally return an RDD. Adapter class. Python. Class legacy database adapter, Spark data source. Def underscore underscore init underscore underscore, self, legacy underscore DB underscore API. Self.legacy underscore DB underscore API equals legacy underscore DB underscore API. Def get underscore data underscore as underscore RDD, self. Legacy underscore data equals self.legacy underscore DB underscore API dot query underscore data, select asterisk from legacy underscore table. Hashtag convert legacy data to a format compatible with Spark, example list of tuples. Adapted underscore data equals, item legacy underscore ID, item legacy underscore value, for item in legacy underscore data. Hashtag in a real scenario, this would create an RDD. Print, adapter, converted legacy data, adapted underscore data. Return adapted underscore data hashtag normally an RDD. Spark pipeline integration. Python. Legacy underscore DB equals legacy database API. Adapter equals legacy database adapter, legacy underscore DB. Hashtag in a real scenario, Spark would use the adapter as a data source. Spark underscore data equals adapter.get underscore data underscore as underscore RDD. Hashtag now Spark underscore data would be an RDD and could be transformed. Benefits. Compatibility. The adapter makes the legacy database compatible with the Spark pipeline without modifying the legacy system. Decoupling. The Spark pipeline is not tightly coupled to the legacy database's API, making it easier to replace or update the legacy source. Maintainability. The adapter encapsulates the conversion logic, making it easier to maintain and update. 1. Adapter design pattern, definition and examples Bellatrix blog, Globant. Bellatrix.globant.com. Reusability. The adapter can be reused in other Spark pipelines that need to access the legacy database. Reduced development time. Rather than rewriting the legacy system, or creating a very complex conversion process inside of the Spark code, the adapter simplifies the process. In this example, the adapter pattern enables the data engineer to seamlessly integrate a legacy data source into a modern data pipeline, ensuring data accessibility and pipeline flexibility. Adapter. Adapters allow incompatible objects to be used together. Following the open-closed principle, we can extend class behavior without modifying the class itself. If a micro USB cable class is initially incompatible with USB port, we can create a wrapper class, i.e. an adapter, which makes them compatible. In this case, a micro to USB adapter makes them compatible, similar to how we use adapters in the real world. Class USB cable. Def underscore underscore init underscore underscore self. Self.isPlugged equals false. Def plug USB, self. Self.isPlugged equals true. Class USB port. Def underscore underscore init underscore underscore self. Self.port available equals true. Def plug, self, USB. If self.port available. USB.plug USB. Self.port available equals false. Hashtag USB cables can plug directly into USB ports. USB cable equals USB cable. USB port 1 equals USB port. USB port 1.plug, USB cable. Class micro USB cable. Def underscore underscore init underscore underscore self. Self.isPlugged equals false. Def plug micro USB, self. Self.isPlugged equals true. Class micro to USB adapter, USB cable. Def underscore underscore init underscore underscore self, micro USB cable. Self.micro USB cable equals micro USB cable. Self.micro USB cable.plug micro USB. Hashtag can override USB cable.plug USB, if needed. Hashtag micro USB cables can plug into USB ports via an adapter. Micro to USB adapter equals micro to USB adapter, micro USB cable. USB port 2 equals USB port. USB port 2.plug, micro to USB adapter. Bridge pattern use case, data pipeline component flexibility. Let's imagine a data engineering team building a complex data pipeline. This pipeline needs to process data from various sources, example databases, APIs, files, and write it to different destinations, example data warehouses, message queues, file systems. Problem. Tight coupling. If the data processing logic, abstraction, is tightly coupled with the specific source and destination implementations, any change in a source or destination would require modifications throughout the pipeline. Code duplication. Similar processing logic might be repeated for different source-destination combinations, leading to code duplication and maintenance issues. Scalability and flexibility. Adding new sources or destinations becomes cumbersome and time-consuming. Solution. Using the bridge pattern. The bridge pattern allows us to decouple the data processing logic, abstraction, from the specific source and destination implementations. Implementation. Abstraction, pipeline processor. Define an abstract pipeline processor class that represents the core data processing logic. This class will have methods like read data, transform data, and write data. Instead of directly implementing the source and destination logic, it will hold a reference to data source and data destination interfaces. Python. From ABC import ABC, abstract method. Class pipeline processor, ABC. Def underscore underscore init underscore underscore, self, source, destination. Self.source equals source. Self.destination equals destination. Add abstract method. Def process, self. Pass. Refined abstractions, specific processors. Create concrete pipeline processor subclasses that implement specific processing workflows, example ETL processor, real-time processor. Python. Class ETL processor, pipeline processor. Def process, self. Data equals self.source.read. Transformed underscore data equals self.transform underscore data, data. Self.destination.write, transformed underscore data. Def transform underscore data, self, data. Hashtag perform ETL specific transformations. Return item.upper, for item in data. Class real-time processor, pipeline processor. Def process, self. Data equals self.source.read. Hashtag perform real-time specific processing. Self.destination.write, data. Implementer, data source and data destination. Define data source and data destination interfaces that represent the source and destination implementations. Python. Class data source, ABC. Add abstract method. Def read, self. Pass. Class data destination, ABC. Add abstract method. Def write, self, data. Pass. Concrete implementers, specific sources and destinations. Create concrete classes that implement the data source and data destination interfaces for specific sources and destinations, example database source, API source, file destination, Kafka destination. Python. Class database source, data source. Def read, self. Hashtag read data from database. Return apple, banana, cherry. Class file destination, data destination. Def write, self, data. Hashtag write data to file. Print, F, writing data to file. Class Kafka destination, data destination. Def write, self, data. Hashtag write data to Kafka. Print, F, writing data to Kafka. Usage. Python. Hashtag create source and destination instances. DB_source equals database source. File_destination equals file destination. Kafka_destination equals Kafka destination. Hashtag create pipeline processor instances. etl_to_file equals ETL processor, DB_source, file_destination. etl_to_Kafka equals ETL processor, DB_source, Kafka_destination. Realtime_to_Kafka equals realtime processor, DB_source, Kafka_destination. Hashtag process data. etl_to_file.process. etl_to_Kafka.process. Realtime_to_Kafka.process. Benefits. Decoupling. The data processing logic is completely decoupled from the specific source and destination implementations. Flexibility. Adding new sources or destinations only requires implementing the corresponding data source or data destination interface. The pipeline processor remains unchanged. Maintainability. Changes to the processing logic or source/destination implementations are isolated, reducing the risk of unintended side effects. Reusability. The pipeline processor and source/destination components can be reused across different pipelines. Scalability. The pipeline can easily scale by adding more source and destination implementations. In this example, the bridge pattern empowers the data engineer to build a robust, flexible, and maintainable data pipeline, addressing the challenges of tight coupling and code duplication. Composite pattern use case, building dynamic data transformation pipelines. Imagine a data engineer working on a platform that allows users to define complex data transformation pipelines. These pipelines can involve various operations like filtering, aggregation, mapping, and data type conversions. The goal is to provide a flexible and extensible way for users to build these pipelines. Problem.
You're ready.
Varying pipeline complexity. Pipelines can range from simple single-step transformations to complex workflows with nested operations. Uniform handling. The system needs a way to treat individual transformation steps and composite, nested, transformations uniformly. Extensibility. Adding new transformation operations should be easy without modifying existing code. Solution. Using the composite pattern. The composite pattern allows us to represent individual transformation steps, leaves, and composite transformations, branches, using a unified interface, enabling the creation of tree-like pipeline structures. Implementation. Component, transformation. Define an abstract transformation class or interface that represents the common interface for all transformation operations. This interface will have a transform method that takes data as input and returns the transformed data. It will also have methods to add and remove child transformations, for composite transformations. Python. From ABC import ABC, abstract method. Class transformation, ABC. Add abstract method. Def transform, self, data. Pass. Def add, self, transformation. Pass. Def remove, self, transformation. Pass. Leaf, concrete transformations. Create concrete classes that implement the transformation interface for individual transformation operations, example filter transformation, map transformation, aggregate transformation. Python. Class filter transformation, transformation. Def__init__, self, filter function. Self.filter function equals filter function. Def transform, self, data. Return list, filter, self.filter function, data. Class map transformation,
All right,
transformation.
Just one second, here I come.
Def__init__, self, map_function. Self.map_function equals map_function. Def transform, self, data. Return list, map, self.map_function, data. Composite transformation. Create a composite transformation class that implements the transformation interface and can hold a list of child transformations. The transform method of the composite will iterate through its child transformations and apply them sequentially. It will also implement the add and remove methods to manage child transformations. Python. Class composite transformation, transformation. Def__init__, self. Self.children equals. Def add, self, transformation. Self.children.append, transformation. Def remove, self, transformation. Self.children.remove, transformation. Def transform, self, data. For child in self.children. Data equals child.transform, data. Return data. Usage. Python. Hashtag create individual transformations. Filter underscore even equals filter transformation, lambda x, x% 2 equals 0. Map underscore square equals map transformation, lambda x, x asterisk x. Hashtag create composite transformation. Pipeline equals composite transformation. Pipeline.add, filter underscore even. Pipeline.add, map underscore square. Hashtag apply the pipeline. Data equals 1, 2, 3, 4, 5, 6. Transformed underscore data equals pipeline.transform, data. Print, transformed underscore data, hashtag output, 4, 16, 36. Hashtag create a more complex composite. Complex underscore pipeline equals composite transformation. Complex underscore pipeline.add, pipeline. Complex underscore pipeline.add, filter transformation, lambda x, x10. Transformed underscore complex underscore data equals complex underscore pipeline.transform, data. Print, transformed underscore complex underscore data, hashtag output, 16, 36. Benefits. Uniformity, individual and composite transformations are treated uniformly, simplifying pipeline execution. Flexibility, users can create complex pipelines by combining individual transformations and composite transformations in a hierarchical manner. Extensibility, adding new transformation operations is easy by creating new leaf classes that implement the transformation interface. Maintainability, the composite structure makes it easier to manage and modify complex pipelines. Reusability, individual transformation components can be reused in different pipelines. In this example, the composite pattern empowers the data engineer to build a flexible and extensible data transformation platform, allowing users to create complex pipelines with ease. Decorator pattern, which dynamically adds responsibilities to an object. Here's a use case of how a data engineer would use it. Use case, dynamically adding data validation and logging to a data ingestion process. Imagine a data engineer building a data ingestion pipeline. They have a core component that reads data from a source and performs basic processing. They need to add validation and logging capabilities, but they want to do so without modifying the core component directly, and they want the ability to add or remove these capabilities dynamically. Problem. Code modification, directly modifying the core ingestion component for validation and logging would make it complex and harder to maintain. Flexibility, they need to be able to enable or disable validation and logging based on different scenarios, example development, production. Maintainability, they want to keep the core ingestion logic clean and focused on its primary responsibility. Solution, using the decorator pattern. The decorator pattern allows the data engineer to wrap the core ingestion component with decorators that add validation and logging functionalities without altering the original component's code.